Welcome to our presentation on analyzing hierarchical economic data using Stata. We will explore how to move beyond simple averages to understand individual heterogeneity. This session focuses on linear mixed models, a powerful tool for handling nested data structures commonly found in economics, such as workers within firms or firms within markets. For instance, instead of just looking at the average wage in a country, we can analyze how wages vary for workers within different firms and how those firms perform differently across various markets. To understand why these models are necessary, let's first look at a common issue in standard economic analysis, the independence trap. Standard ordinary least squares, or OLS, regression relies on a critical assumption that all observations are independent. This often doesn't hold true for economic data. As illustrated, if we simply aggregate all data points, we might incorrectly conclude there's no relationship between variables like experience and wage, appearing as a flat line. This is the independence trap. In reality, economic data is frequently hierarchical. Think of workers nested within firms, or states nested within regions. Observations within these groups are not independent. They often share common characteristics or influences. Ignoring this inherent structure can lead to Simpson's paradox. An aggregate analysis can mask true, positive relationships that exist within each distinct group. When we disaggregate, we see the clear positive trends within each subgroup. This highlights why understanding data hierarchy is crucial to avoid drawing misleading conclusions from our analyses. With this understanding of the OLS limitation, let's now explore when and why we should use more appropriate models, specifically linear mixed models. This flowchart helps us navigate the decision of which modeling approach to use when dealing with different data structures. The first critical question to ask is whether your data exhibits a nested or hierarchical structure. If the answer is no, a standard ordinary least squares, or OLS, regression is typically sufficient. However, if your data is nested, the next step is to determine if your research specifically focuses on the individual groups themselves. If yes, meaning these specific groups are of intrinsic interest, then a fixed effects model is the appropriate choice. Now, if the groups in your nested data are actually a random sample drawn from a larger population, you then consider whether you need to model both group-specific slopes and intercepts. If you only need varying intercepts, a random effects model, intercept only, might suffice. But if the answer is yes, you need to account for heterogeneity in both the starting points and the effects of predictors across groups. Then linear mixed models, or LMMs, are the most powerful and flexible approach. This allows for a much richer understanding of your data, moving beyond simple averages to capture nuanced group-level variations. Stata offers a sophisticated ecosystem of commands for implementing mixed models, which have evolved to meet diverse analytical needs. In the past, the XT-mixed command was widely used. While it's now considered a legacy command, it remains functional for those working with older Stata versions or replicating historical analyses, though it has limitations for modern post-estimation techniques. The current standard and true workhorse for models with continuous outcomes is the mixed command. It's highly powerful and flexible, supporting various estimation methods like REML and MLE, along with complex covariance structures. This is what you'd use for modeling something like wages nested within firms. For more specialized applications, Stata provides MEGLIM for generalized linear mixed models, such as those with binary or count outcomes, like the probability of a worker leaving a job. Additionally, MENL is available for tackling nonlinear mixed effects relationships. Understanding this progression helps us choose the right tool for our specific data and research questions. The mixed command itself offers crucial choices in estimation methods, which we will explore next. The core equation for a linear mixed model looks like this: y equals x beta plus zu plus epsilon. Let's break it down. The first part, x beta, represents the fixed effects. This is the global truth, or the population average relationship, similar to what you'd find in a standard regression. The second part, zu, represents the random effects. This captures the local deviation for each specific group. Instead of estimating a separate coefficient for each group, we estimate the variance of the distribution from which these group effects are drawn. Finally, epsilon is the residual error, representing the observation-level noise that isn't explained by the fixed or random effects. In a wage model, X beta might capture the average return to education across all firms. ZU would capture how that return to education deviates for each specific firm, and epsilon would be the unexplained variation for each individual worker. Like any statistical model, LMMs rely on a set of core assumptions to be valid. Let's review them. Like any statistical model, linear mixed models rely on a set of core assumptions for their validity. Let's review the main three. First, we assume linearity. The relationship between our predictors and the outcome variable must be linear at the fixed effects level. Second is normality. Both the random effects, denoted by U, and the residuals, epsilon, are assumed to be drawn from normal distributions with a mean of 0. Their respective variances are represented by G and R. This is crucial for accurate inference. Finally, we have independence. We assume that groups themselves are independent of one another. However, it's important to remember that data within these groups is allowed, and often expected, to be correlated. For instance, student performance in one school is independent of another school, but students within the same school might have correlated performance. With these assumptions in mind, let's explore what random effects mean in an economic context. When we build linear mixed models, understanding the economic meaning behind our random effects is crucial. This slide illustrates two key scenarios. On the left, we have a random intercept-only model. This suggests that different groups, such as rich versus poor states, might start at different economic levels, but critically, they all grow or react to a given factor at the same underlying rate. The parallel lines on the graph visually represent this shared growth rate, with only their initial starting points varying. Moving to the right, we see a random slope and intercept model. This is a more flexible and often more realistic scenario. Here, not only do groups start at different levels, but they also react differently to incentives or changes in variables. For example, capital investment might work better or have a different impact in some regions compared to others, leading to varying growth rates. The non-parallel intersecting lines clearly show this divergence in slopes, indicating that each group has its own unique response pattern. When working with mixed models, a crucial decision is whether to use restricted maximum likelihood, or REML, or maximum likelihood, ML, for estimation. REML is the default in Stata for linear mixed models and is generally preferred for smaller sample sizes. Its main advantage is providing unbiased estimates of the variance components, which is vital for accurate inference about random effects. However, a key limitation is that you cannot use likelihood ratio tests to compare models that have different fixed effects. On the other hand, ML, or maximum likelihood, is more suitable for large samples and is essential when your goal is model comparison. It allows you to perform likelihood ratio tests to compare nested models, particularly when they differ in their fixed effects. The trade-off is that ML variance estimates can be biased downwards, especially in smaller samples. Therefore, your choice depends on your primary objective. Prioritize unbiased variance estimates with REML for small samples, or use ML for robust model comparison in larger datasets. To put our understanding of linear mixed models into practice, Stata's mixed command is your primary tool. The syntax follows a logical structure. It begins with mixed, followed by your dependent variable, then the independent variables that constitute your fixed effects portion. This part is essentially a standard regression. The crucial element is the double pipe separator, pipe. This clearly delineates the fixed effects from the random effects specification. After the double pipe, you specify your grouping variable, such as firm ID, followed by a colon. Following the colon, you list the variables for which you want to estimate random coefficients. If you want a random intercept only, you simply leave this part blank. Finally, you can add various options, like MLE or ReMel to choose your estimation method, or coefficiency to specify the random effect structure. For instance, the example mixed wage education, pipe, firm ID, education, ReMel, models wage as a function of education, allowing both the intercept and the slope of education to vary by firm ID, estimated using restricted maximum likelihood. When specifying random effects in a linear mixed model, a crucial decision involves choosing the covariance structure for these effects. We have three main options. First, the independent structure is often the default, but it assumes that your random slope and random intercept are completely unrelated. This is a strong assumption and may not always hold true in economic contexts. Second, and generally recommended for economics, is the unstructured covariance. This option is far more flexible. It allows the random slope and intercept to be correlated, which is often a more realistic scenario. For example, a high starting GDP in a region might imply slower subsequent growth, indicating a correlation between the random intercept, initial GDP, and the random slope, growth rate. Finally, the identity covariance structure is quite restrictive, assuming all random effects have equal variances and are uncorrelated. This is rarely appropriate unless you have very specific theoretical reasons. Given these options, the unstructured approach is typically preferred in our field, as it accommodates the complex relationships often found between random effects. Before we can run these commands, we need to ensure our data is in the correct format. Mixed models in Stata, which we're discussing throughout this presentation, require data to be in long format. This means that each individual observation, such as a firm's profit in a specific year, must occupy its own separate row in the dataset. Often, economic data is initially collected in a wide format, where a single row represents a subject, like a firm, and different time periods are spread across multiple columns. To convert this, you can use Stata's reshape long command. For instance, if you have profit data for a firm across several years, like profit 2020, profit 2021, and profit 2022 as distinct columns, the command reshape long profit, I firm ID, J year will transform this. It creates a new variable called profit containing the values, and a year variable to indicate the original column, ensuring each firm year observation is a unique row. This preparation is essential before fitting any mixed models. Our first practical step in building a mixed model is to run an empty, or null, model. This model includes only random intercepts for our grouping levels, without any fixed effects predictors. Its primary purpose is to calculate the intra-class correlation coefficient, or ICC. The ICC quantifies the proportion of the total variance in our outcome variable that can be attributed to the hierarchical grouping structure. A high ICC indicates significant clustering within groups, confirming that a mixed model is indeed necessary. In this example, we're modeling gross state product, or GSP, nested within states and regions. The ICC for the region level is 0.159, meaning approximately 16% of the total variance in GSP is due to regional differences. Furthermore, the combined ICC for state within region is 0.851, showing that a substantial 85% of the variance is explained by this two-level nesting. This strongly confirms the importance of accounting for these hierarchical structures in our analysis. Our second practical step involves adding fixed effects predictors to our mixed model. As shown in the Stata command, we simply list our independent variables, such as GSP, private capital, employment, highways, water, other, and unemployment, after the dependent variable but before the double pipe separator. These coefficients represent the population average effects across all groups, much like in a standard OLS regression. Looking at the results, for instance, the coefficient for private capital is 0.267. Since both the dependent variable, GSP, and the independent variable, private capital, are log transformed, this coefficient can be interpreted as an elasticity. This means that, on average, a 1% increase in private capital is associated with a 0.27% increase in gross state product, all else being equal. We now have the average effect of these factors, but the next question is whether these effects vary by region or state. To answer that, we'll need to consider adding random slopes. We've confirmed the overall average effects. Now let's explore if these effects vary across groups by adding random slopes. The hypothesis we're testing is whether the return on private capital differs by region. We implement this in Stata using the mixed command, mixed GSP, private, emp, $region, private, cove unstructured, REML. Here, private is added as a random slope at the region level, and we specify an unstructured covariance for flexibility, using REML estimation. Looking at the output for random effects parameters, the variance for private is estimated at 0.045. A non-zero variance like this confirms that there are indeed regional differences in the returns to private capital. Additionally, the covariance term, 0.062, indicates a correlation between the base GSP and these regional capital returns. To formally test if this random slope significantly improves the model, we would use an LR test to compare it against a model without the random slope. After fitting our mixed model, the next crucial step is to visualize the estimated random effects for each group. We achieve this using post-estimation commands to predict these effects, which capture the deviation of each group from the overall population average. This slide presents a caterpillar plot, an effective way to display these predicted random effects along with their confidence intervals. The central dashed line represents the overall average effect, which is 0 on this plot. Regions whose confidence intervals do not cross this line indicate a statistically significant difference from the average. As we can observe, the Northeast region stands out with significantly higher productivity compared to the national average. Conversely, the Pacific region demonstrates significantly lower productivity. For all other regions, their confidence intervals overlap with the 0 line, suggesting their productivity is not statistically different from the average. This visualization powerfully highlights the individual heterogeneity that our mixed model is designed to capture, moving beyond aggregated averages to reveal group-specific patterns. As we conclude, let's recap the key takeaways from our discussion on linear mixed models. First, hierarchy matters is a foundational principle. It's crucial to use LMMs when dealing with nested data to accurately model the structure and avoid misleading conclusions, such as ecological fallacies. Second, model building is an iterative process. We recommend starting with random intercepts and then strategically testing for the inclusion of random slopes, using likelihood ratio tests, ensuring each addition is theoretically justified. Third, for estimation, remember the strategic choice. Use restricted maximum likelihood, or REML, for accurate variance estimates, especially with smaller samples. Switch to maximum likelihood, ML, when you need to formally compare models with different fixed effects. Finally, for those wishing to delve deeper, we recommend multi-level and longitudinal modeling using Stata by Rabe, Hesketh, and Scrondel, and the Stata manual section on ME mixed models. Ultimately, mixed models provide us with the invaluable ability to simultaneously observe both the broad forest of population trends and the unique trees representing individual heterogeneity within our data.